Thank you very much. And yes, also thank you very much for spelling out our title. That might sound a little vague, but I'm extremely happy to have you all here and to talk to you about Onyx, a technology that I am personally very excited about. I'm pretty sure Kuba is as well. And we at Quantco are also extremely excited about it. It really has become a bit of a cornerstone technology, actually, at Quantco over the last 12 months. Some people might recognize we actually also had a talk last year at PyData here. That one a year ago was more high level, generally introducing the technology. This talk today really, we want to drive home the point that it is production ready. We are actually using it in production in large scale projects, and we are extremely happy and, as I said, extremely excited to talk about it. So, how are we going to go about spreading this kind of excitement? So the first step, we are just going to walk through the standard life cycle of a machine learning project that many of you might be familiar with. And then from there, we will see that in the beginning, it's all great. But then later, especially when you come towards the deployment side, actually, you probably might be running into problems, or you probably have some personal experience running into problems. And that is really where this technology Onyx comes into play. And at that point, we then also will tell you why we think that the library we've actually just open sourced a few weeks ago called Spox is really filling an important void in this regard. Yes, so let's jump into the life cycle of a machine learning project. So we are here at a Python conference. So probably what you're going to do as one of the very first steps, you're going to define your very model. You're going to define a pipeline. You're going to define your feature engineering. You're obviously going to do it in Python. And the world is great. Like, we want to have this rapid development lifecycle. We want to visualize some data. We want to use pandas. Really, Python is extremely hard to beat in this early phase of a project. And yeah, while we define our model, we really write it into source code. And within the source code essentially lives in our training environment. So we have other dependencies. We might, for example, have LightGBM, etc. So that is sort of the dotted line here. This is like an environment with like further dependencies. Now, of course, we are not happy just defining a machine learning model as source code. Of course, what we really want to do is we want to train it. We want to train it on our training data. So the next step is, well, training. So we take our data, we call fit or whatever our framework sort of provides, and then we end up with our trained model in our Python process memory. So now it's a very, very complex object that just resides in the memory. And then, of course, we probably never want to deploy directly from our training process, like the training and the inference or the deployment is pretty much always like a separate step. So we somehow need to now put this into some kind of artifact that we can then sort of ship around. If you look at the scikit-learn documentation online, for example, you will see that, well, what they are actually doing, or what is sort of the official recommendation is, well, call pickle. It's built in, and then you get like a pickle file. Honestly, I think it's, to some extent, extremely amazing that you can do this with Python in the first place, that you can just dump a model generically. But I put a question mark here because, well, while it's actually kind of amazing, it does come with a lot of problems, as we will discuss in the next slide. Namely, yeah, what pickle does is like it only dumps the state, does not dump the logic. So if we actually then want to load the pickle file and then run the inference with our model, we have to maintain this entire training environment. We have to recreate it on our inference side. So one way of doing this, of course, is we could just wrap this in a Docker image and essentially bake it. But again, this also comes with some issues. Now, this does take me then to the next and, well, potentially last step of the development lifecycle, namely, OK, we want to deploy it. I just mentioned it. We probably, a common approach would be to pack it into a Docker container or something. But what kind of issues may we then sort of encounter during deployment? And this is then also a bit of the solution we want to present. So I belabored the point already quite a bit. Pickle comes with problems. So now we have wrapped everything. We need to recreate the training environment pretty much exactly in the way we had it during training at the inference part. And now, instead of just saying like, oh, here's one file, just run this, and you're good for your deployment, you now have to say like, oh, here's an entire container. It is very difficult to distribute just because it's like a file plus an entire environment, a pickle file plus the entire environment. Now, more or less a corollary of sort of these pickle issues is it's not only difficult to distribute your model, it's also difficult to archive. So for example, with Quantco, we often have the problem, or not a problem, but like it's a requirement that our models need to remain online for like a long period of time. So order of magnitude, like several years. And now if we sort of just really bake all the dependencies from our training time into our container, this can create a lot of security issues, for example, if we can't update dependencies. It is also a problem if we want to compose a model. So for example, we have two models trained at different times. Now we want to compose them in like one Python process. That's pretty difficult if the two pickle files have different dependencies. We just can't do it. And then same again, we sort of, if we want to keep our intellectual property that was used for training out of the deployment, again, if we do it with pickle, we're out of luck because we have to pretty much ship everything. But even if we find solutions for some of these problems, all of these problems that I'm going to show here have individual solutions, to be fair. Even if we find problems to sort of work around pickle, we might actually still run into like some more fundamental issues. Like for example, this is actually what really got us as Quantco onto the Onyx track is it might just be that running your Python model, your scikit-learn model is just too slow. So in our case, we had like some very strict latency requirements, and our model, while not being like per se super slow, it was just an order of magnitude at least too slow. And then switching to Onyx, as I will explain later, we got several orders of magnitude as a speeder. So yeah, if your performance is too slow and you started with the Python tool stack, at that point it might just be a bit inconvenient. But that might not actually be all. So maybe you could also see like a scenario where, okay, you've trained your model, but now you actually want to deploy it not on like some server where you have Docker. Maybe you want to deploy it on a mobile, within a mobile app or something. And there, of course, you can't really just run Python easily. So you would need to like somehow export it. And all of these issues, again, have maybe individual solutions, but there's actually one way that we can really solve them elegantly all together. In order to figure that out, let's take a step back. Why is this so hard? Why do we have this problem with machine learning models, how to distribute them, etc., while the rest of the software engineering world seems to have figured out how to distribute software decades ago? So let's take a look how everybody else is doing it. For non-machine learning related software, we might have something like this. We start off with source code. Let's say it's Java. And now we have a compilation step. Again, this is somewhat in a compilation environment. There's probably like some very, very complex objects floating around during the compilation process. But then at the end we really arrive with some artifact that is more or less, or like pretty much completely independent from the environment used during compilation. And we can now vendor this artifact very easy. It's very easy to deploy. Again, this is in the non-machine learning process. Now, let's contrast that with machine learning. So I've shown part of this before. We start with our source code that defines our pipeline. We have our data. We have a training step. And then we end up with this trained model, a big blob in the Python process. And now what we kind of want to do is very simple. We want to have a magic step. We want to have some way to like compile this big object in our Python memory into some artifact that now is outside of our training environment, not inside anymore. So that when we deploy it, we just need to grab this one binary file, put it somewhere. It's actually, who here actually was at the WebAssembly talk just before? Very few. Bummer, because technically it's what WebAssembly would also solve. Well, okay, but we really want to have this one binary file that we get, and then we deploy that. So I'm pretty sure you might have some questions about this magic step, but just to sort of say, okay, why is this all worth the trouble? I actually, before getting to the magic step, and Kuba is actually going to explain that in detail in a moment, I just want to say, like, okay, what is it that makes it so great to have the artifact outside of the training environment? So let's look at what the deployment actually looks like. Ah, yeah, sorry. So the solution to all of this is, you might have guessed it from already being mentioned like several times. This artifact is a standard. It's an open source standard. It's around since a few years. It's called Onyx. And whenever in the following slide you see something called model.onyx, that is actually the artifact. This is this binary file. This is the holy grail we are actually attempting to get to. Yeah. All right. So what does the deployment look like? Let's get that out of the way first. Bam. This is how easy deployment could be. Like, there is no Docker, no nothing. This particular example is in Python, but it could be any other language. We need a runtime where we load this artifact, but it's our only dependency, this runtime in this particular case. It's completely written in C++. It has bindings for pretty much any language under the sun, including WebAssembly. Unfortunately, not a lot of people were in that talk. The way it works is essentially you grab this runtime, you create an inference session, you just point it to this file. Again, this is the only file you need to distribute. There is no other dependencies. Like, you don't import your pipeline anywhere. And then when you want to do inference on your model, you get your inputs as NumPy arrays, you throw them at the session, and this is your outputs here. That's it. And in this case, it's Python, but again, it could be from C, it could be from Java, it could be from WebAssembly, it could be anything. So this is really, really, really nice for deployment. Now, about this magical step. We have our trained model, we have the magic step, and then we arrive at Onyx. How can this possibly work? So the idea behind this Onyx standard, and we don't want to get too much into the details of Onyx itself, but the core idea really is we have a set of standardized operators, just like NumPy. NumPy has like NumPy sum, NumPy matmul, and so on. And we just have a sequence of these operators where we have like inputs, and then the outputs lead to the next set of operators, and eventually we arrive at the outputs we like. Yeah, and then Pickle, previously I mentioned it. What Pickle does, it only serializes the weights of our trained models, only the state, but the logic lives somewhere else. Now, if we serialize something that is defined in this standard with the Onyx operators, we serialize the logic needed for the inference along with the state, and this is really the crucial difference. All right, now let's get a little, before we get hands-on, let's actually take a step back. Let's see what actually is around in the Onyx ecosystem. I mentioned it before, it's not completely new. There are quite a few projects around it, and let's take a step back to see where we are at.
Cool.
And Kuba is going to do that.
So let's look around the whole Onyx ecosystem and sort of what do we have, what are we dealing with. So as Christian has shown, sort of the image we have right now of Onyx is, well, I got Onyx from somewhere, maybe it's this primordial being is just here already, and we can use it in runtimes. So for instance, you have different runtimes. For instance, there's the mainline Onyx runtime, which is quite widely supported. You have other runtimes you may want to use if you target a different platform, like Tract for embedded devices. And so now let's think about where does Onyx actually come from. So in the scope of this, we are sort of looking at different machine learning frameworks. We're getting models in those machine learning frameworks that we trained, and now somehow we have to get them into Onyx. So this process is called conversion. So the way it's done is that we implement converter libraries, and those converter libraries take care of taking a model object in Python and converting it into Onyx. So the way this is done currently in those like quite big libraries which have already accumulated good coverage of Onyx converters, basically, is that essentially every one of them has its own way of doing it. And that's not great, because writing Onyx, from the ground up, it's not quite easy because it's quite a low-level IR. So it's quite a low-level language in a way. So what we've done in this space is we introduced Spox. And Spox is this new way of writing Onyx yourself. As you will see, it's actually quite composable. It leaves you with a lot of headaches that you would get if you were writing this yourself. And with Spox, you can create your own converters from your own frameworks, your own libraries, or just libraries that do not have converters yet. And you can implement that conversion into Onyx. All right, then. So let's look into expressing some models with Spox. So in Spox, well, we're going to be converting different pipeline components, so different smaller model pieces essentially. So let's think about sort of an sklearn-oriented example, since that's quite close to home for us. And for instance, we have a linear regression, sort of scikit-learn-like. So there's some initialization code, private things we don't really care about. There's a fit method that we assume will have already been called when we get to the conversion step. So there's some fit. And what we really care about is sort of how does predict look? How does the inference logic look? So here, we're consuming an array, producing an array, and there's some matrix multiplication with our coefficients as fit, and we add an intercept value. So we can see that there's some trained weights. Those are the attributes essentially of this model, and there's some simple NumPy operations we're doing on that. So that's a simple view on that. That's sort of going to drive our example. So now let's look into how we can structure a Spox converter. So this code here is really just a bit of boilerplate to sort of say what we're doing. So a converter is sort of this class for us where we create the converter for a given pipeline component. So here we call it a model. So the linear regression is this sort of component, this model. And we give the converter access to it. Because we are still in Python, we want to be able to access all that same state, all those attributes. Now, the nice thing we're going to do is actually replicate the same sort of interface the linear regression object has with the converter object, with the Spox sort of version of it. So this predict method is going to take this var object, which I'm going to explain in a second, and return some new var. So now what is var? In Spox, we sort of abstract away the fact that because we're describing sort of the inference logic, there's no concrete runtime value. There's no array to speak of. So instead, var represents this variable, this lazy value that will exist at runtime. Here, we're just sort of thinking about it abstractly, that we're going to be applying some operations to it, getting some results out, and all those results are going to be variables. So in this specific case, we're going to say the variable is an array. It's just a lazy array. It doesn't have concrete values. All right, then. So let's look at how the prediction logic looks. So this is it. It's quite explicit, but it's actually quite simple to sort of dissect. So first of all, there's this op I've introduced here. So Spox sort of exposes for you these Onyx operators, those standardized operators Christian was talking about. And those are exposed in the op module. They are quite similar to NumPy. There's a lot of them. There are domain-specific ones for deep learning or computer vision, but also quite basic ones like arithmetic here. So that's the first thing to notice. So we have an addition and a matrix multiplication happening. And we also have these const calls. So what's happening is that we're accessing self.model, so our converted model, and the state of that model as trained, so those trained weights. And we are, this const call, this constant operator, is explicitly taking those weights and moving them into our Onyx model, essentially. We are saying this is part of the model. We're moving it into a variable. And this way, we essentially express the entire logic, this matrix multiplication with the coefficients and addition of an intercept value. And this same exact idea applies to a lot of different converters you can have. So pre-processing components like scalars or different ways of imputing data and so on. This sort of same concept applies. So moving on, if we sort of have those basics, this actually applies, this same level idea in Spox applies to, well, more high-level things. So for instance, let's think, OK, so we've defined these converters. Now I want to have an arbitrary model and just ask for a Spox converter for it. So I'm going to write this function called converter. It's going to check, OK, what kind of model is this? I'm going to return the appropriate, dispatch the appropriate converter. So say I've got this now. So for instance, a quite useful sklearn concept is pipelines. So in pipelines, we're going to define the converter for a pipeline, and what a pipeline does, this is going to be essentially what you're looking at. It's essentially the same implementation as in scikit-learn. So a pipeline is defined. It has a bunch of steps in it. It takes the data at the start, and it applies all the steps in the pipeline consecutively. It transforms the data as given. And then for the last step, it says, oh, that's an estimator. I'm going to take this pre-processed data, give it to that estimator, so I'm calling predict there. And I get my result out, the result of this pipeline. And that's basically that. So here, really the only difference, the only Spox thing that's happening is if you look here, I place this converter call. So step itself is a Python object representing a model. so scikit-learn-like, but converter sort of, dispatching the right converter for it. So we are getting the Spox version. And because we follow the same interface as the scikit-learn does with Spox, so we have a transfer method, we have a predict method which takes a single value, we get what we want, essentially. We just apply all those steps consecutively, but we apply the Onyx versions of them. And that's quite cool, since this is quite a extensible approach of doing it. All right, so let's sort of now think, OK, but I'm sort of talking about these variables and like, well, we got these magical objects, we're applying operations to them. Where did they come from? And like, I mean, for this, let's start thinking about first, like, how do we get to this point where we actually can convert a model? Well, to do this, first we are actually, training the model. I defined here a very simple pipeline, quite trivial. We have a scalar, we have a regression, and I'm fitting that pipeline with some training data, essentially. And that's done. Now, I can be anywhere else in that Python, process. And at this point, I'm going to start thinking about how I'm going to do my Onyx conversion. So I'm going to get some Spox imported. So these are a few utilities that are going to be useful. And I'm going to access my converter library that I implemented using Spox. So this is just represented in this converter function as defined on the previous slide. So var was this placeholder for data. And Onyx is actually strongly typed and statically typed as well. So the way we're going to say, oh, this is like a variable, this variable is going to arrive at runtime, we're going to introduce something called an argument. An argument is just a placeholder for data of a given type. So say here I have a tensor type, which is just a fancy way of saying array in this case. And it's a float64 array, which is just a vector. It has a single dimension, some size n. And as I have this placeholder now, this x, which is a variable, I can give it to the pipeline, to the converter of the pipeline here, and I get my y out, which is the result of this pipeline. This is the result of my model. This is what I want to essentially compute from x, where x is some input. And the way Spox allows you to wrap this up is you say, OK, so my model inputs I want, my argument essentially is this x. I'm going to call it x. We have to say, since in the model we sort of say, oh, these are the inputs you have with these names, and these are outputs you get with these names. And yeah, in build we say, OK, x is my model input, y is my model output, and model becomes this special Onyx object representing the computation, representing the model. And at this point, we've done serialization. All the dependencies are gone. Model is just this, essentially a representation for a binary object, and we can just go onyx.save, we save it into a file, and it's done. And how does being done look? For Onyx, it looks something like this for the super basic pipeline. You can actually visualize it as this sort of DAG, as a sort of graph, this task graph in a way, if you maybe use Dask, or maybe if you use PyTorch or TensorFlow, those are in a way layers. But these operators are much more primitive. So for instance, you can see around the sort of main path, you see the constants. So those are the model weights that we had. So now they are explicitly serialized within the model file. And we have, addition, multiplication, those came from the scalar, and matrix multiplication, addition, those come from the regression. And so if we applied all of these operators, all the dependencies from Python are stripped out, and we are left with just this computation itself. And with that, we have the product, and Christian will summarize what we've got.
Yes, thank you very much. All right. So, quick summary. What do we think? Why are we so excited about Spox? Why are we so excited about Onyx? So in general, it's a tool. Onyx is a tool to compile your trained machine learning model into something self-contained. And it might not be obvious immediately, but it's an extremely, extremely powerful approach actually to solving a whole host of issues. Now, well, those issues are you get very stable, very, very fast, and very maintainable deployment. And what we really, really want to stress with this talk, this is production ready. It's not like, oh, some fancy pants technology somewhere at the horizon. This is actually here. This can be used. And it has strong corporate backing. Original Onyx is developed and pushed by Microsoft, but by now it's also NVIDIA, IBM, etc. Behind it. And it really has been a key technology at Quantco for now more than 12 months in production. And everything we've presented here is open source. So if you're interested and share some of the excitement, check out this link for Spox, where you find some more documentation and tutorials, etc. Thank you very much.
Thank you.
Very cool insight. Very cool. So thank you very much for your talk. I got one question which is almost the same as two other questions on Slido. So how do you deal with pre-processing steps in Onyx models? Because it's an important part of AI models to get the data into a form how the model is trained on. So is there a solution in Onyx?
Yes,
or in
I'm actually very glad then if that was unclear that the question came, because you can, well, I guess here it, well, wherever. So the point really is, okay, I don't find the slide now. The point is, it's not only like the tree ensemble regressor at the very end, it's your entire feature engineering pipeline. There are like about 180 standardized operations in the Onyx standard, where it's just, you get inputs, something is being done to them, like for example, you encode, you impute, whatever, you clip. All of these have standard operations in the standard. You can do your entire feature engineering pipeline. So in our production use case, we have models with thousands of nodes, and it just works. And yeah, so it's really end-to-end.
Cool. And another question is how to convert to ONNX if an operator of a model neural network is not implemented in ONNX and an unknown placeholder is returned.
Great question. We also have something for that. Well, this one is a bit more generic, but there's several mechanisms for dealing with this. One of them is essentially custom operators. So the standard is extensible. There are ways of saying, OK, I'm going to provide this operator. I'm going to call it this and this. And then various runtimes are supposed to provide ways to essentially link those implementations. So Onyx runtime allows you to link a dynamic library. You can implement your own custom operators. Then you're sort of dealing with that as well. In terms of expressibility, you can actually express a lot with Onyx because it actually gives you full-blown control flow, which Spox allows you to use. So you can handle, if you have like operators which don't exist, which require just simple branching, or even if they require like complex looping, then you can actually express a lot of things. So for instance, we had experiments where there's no join implemented in Onyx. Well, we can do a custom operator, or we can prototype an implementation with a loop essentially, and re-implement like a known algorithm. And that's still more efficient than pure Python. So yeah, there are ways of dealing with that.
Cool. Thank you very much. The time is over. There's still questions there on Slido and perhaps also in the room, but I think you're around here. So just directly talk to the speakers, I think. And again, applause.
Thank you very much.
Thank you very much.